This is an application of the observations that solar activity is declining and the corresponding interplanetary magnetic field is decreasing. We were actually studying the magnetic fields in the Heliosheath, which, by the way, are very weak, and we surely don't want any weaker magnetic fields out there, so I hope Janet's wrong about that. But we were expecting to see that the magnetic... Okay, next slide. We were expecting to see that the magnetic field strength would increase with increasing distance into the Heliosheath, that is to say, with increasing time. So the top panel shows the magnetic field strength measured by Voyager 1 from just behind the crossing of the termination shock in 2005 out as far as we have processed the data in 2008.8. And as I said, we were expecting, based on quasi-stationary models of the Heliosheath, that the magnetic field strength would increase with increasing time. And we found that, in fact, it's decreasing. So the question is, why should the magnetic field strength be decreasing with something missing in those models? I'm going to come back to that question, but since I have this slide showing the angles, I want to digress a moment to show that here is the azimuthal angle of the magnetic field as a function of time. You can see a sector pattern over here, but around 2006.23 or so, you start to see basically a unipolar field with some exceptions. And the reason for that is shown on the next slide. This is the maximum latitude of the heliospheric current sheet that was computed from solar magnetic field observations by Neil Sheely and Yiming Wang. They calculate the neutral line on the source surface, and then we just project it out to the position of Voyager. And what this says is that there was a change at about 2006.3 or so, in which the heliospheric current sheet dropped below the latitude of Voyager 1. And that would explain the unipolar regions that the uniform polarity that we saw after that time. So basically this tells us that we should have been below the spacecraft should have been above the heliospheric current sheet after that period of time. Those occasional exceptions of the polarity to what we expect here are presumably due to northward flows that were observed in the Heliosheath. Next slide. Now I'm returning to the question of why we didn't see the magnetic field strength increase with time and distance in the Heliosheath. And just to orient you, these are the last sunspot numbers for the last 3 solar cycles. These are the magnetic field strengths observed at 1 AU during the last 3 solar cycles. And now you can see these are basically yearly averages. This is the cycle that we're currently in. And you can see that the field is decreasing to very weak values. This is 4 nanoteslas at 1 astronomical unit, which is probably the weakest we've ever seen. And you can see that a 1 nanotesla field would be pretty dramatic on a scale like this. The next slide shows this last panel just repeated. This is the current cycle. And the important thing here is that I've shifted it to this position of Voyager 1. So I've shown the Voyager 1 observations of the magnetic field strength here. And at this point, there's a termination shock where we see the uniform fields that I described. But before the termination shock, you can see that the magnetic fields at 1 AU were basically reproduced at these very large distances of 100 astronomical units. So you might expect that to happen in some respect afterwards. So here, when we were in the Heliosheath, the magnetic field at 1 AU was decreasing, and we should really take into account that decrease. In other words, while we're in the Heliosheath, expecting to see an increase in the magnetic field, there's a temporal effect that we have to consider because of this peculiar solar cycle. The next slide shows how we actually make this correction. You have to basically calculate what the field should be doing in front of the termination shock. And for this purpose, I use Parker's model of the magnetic field as a function of time or distance. His curve was a solid curve which follows the predictions the observations very well. These are the dots. And the extrapolation for the magnetic field while we were in the heliosheath is shown here. So you can see, indeed, there was a tendency for the magnetic field strength to decline in the absence of a termination shock. And you do have to consider that decreasing solar activity effect, the decreasing magnetic field strength, when you're calculating the radial gradients of the heliosheath magnetic field. So we take this observed nearly constant, slightly decreasing magnetic field, we correct it for the changes in the magnetic field expected as a result of the decreasing solar activity, and we arrive at the result in the next slide. There is indeed, after you make this correction, a radial gradient of the magnetic field strength, and the magnitude of this radial gradient agrees with that which is predicted, for example, by a recent paper by Pogarelov et al. So indeed, the magnetic field strength, if you consider it quasi-stationary conditions, is increasing as we move through the heliosheath toward the heliopause. And the next slide shows the summary. This is the gradient of the magnetic field. It's somewhere between 0.0017 nanoteslas and 0.005 nanoteslas per AU. As I said, the predictions are consistent with that. I also made that point that V1, Voyager 1, has been above the maximum latitude of the current sheet and observing uniform magnetic fields from the North Polar coronal holes, with some exceptions to